Welcome to the Deep Dive. Today we're looking at this essay by Yurgo Schneepat. It's about quantum optimization for AI models.
Yeah,
And so it's pretty fascinating.
it is. Yeah, it's
It's a really cool look at how this emerging field could, revolutionize the way we build and train AI.
right. Yeah, and I think Schneepat does a good job of laying out how AI is, obviously advancing so rapidly,
Yeah.
but a lot of times it's held back by the limitations of just classical optimization techniques.
Yeah, and, those techniques are really struggling to keep up with these massive data sets and the complex models
Right.
that are becoming more and more common in AI.
Yeah, exactly. And that's where quantum optimization comes in.
Yeah.
Schneepat really argues that it has the potential to just overcome all these challenges and unlock a whole new level of AI performance.
Okay, so before we get into specifics, can you give us a quick primer on what makes quantum optimization so special?
Sure.
We've all heard of quantum computing, but how does it actually apply to optimization problems?
So at its core, it really leverages these unique properties of quantum mechanics, so things like superposition and entanglement, to explore these potential solutions much more efficiently than classical methods.
Can you elaborate on that a little bit? How does exploring solutions in this quantum way lead to better results?
Well, imagine you're trying to find the lowest point in this huge mountainous landscape, right?
Yeah.
A classical computer would have to climb each mountain peak, one by one, to find the lowest valley. A quantum computer can explore multiple peaks simultaneously thanks to superposition. It's like having a team of climbers instead of just one.
So it's like massive parallel processing,
Right.
which is obviously a huge advantage when you're searching for optimal solutions.
Absolutely.
What about entanglement? How does that factor into the equation?
So entanglement allows these qubits to be linked together in a way that lets them influence each other instantaneously, regardless of distance.
Oh.
And this interconnectedness can be harnessed to explore relationships between variables in an optimization problem that would be impossible for a classical computer to grasp.
Wow, that's pretty incredible. So Schneepat's essay delves into several specific quantum optimization methods that could be applied to AI. One that I thought was really interesting was quantum gradient descent,
Yeah,
or QGD. It sounds like a quantum twist on a classic optimization algorithm.
it is. So classical gradient descent works by iteratively adjusting the parameters of a model to minimize a cost function. QGD leverages quantum parallelism to evaluate multiple potential parameter updates simultaneously, which can speed up the process of finding the optimal set of parameters.
So instead of taking these tiny steps down this optimization landscape,
Yeah.
QGD can take giant leaps,
Yeah,
exploring multiple paths at once.
exactly.
Okay, that's a really powerful concept.
Yeah, and Schneepat also talks about quantum annealing, which is particularly well suited for solving a class of problems known as combinatorial optimization problems. These problems involve finding the best combination of variables from a vast set of possibilities, something classical computers struggle with.
So it's like trying to find the most efficient route
Right.
for a delivery truck with 100 stops.
Yeah.
And you've got to factor in traffic, weather, all these other variables.
Exactly. And actually, Schneepat points to D-Wave Systems as a company making strides in this area. They've developed specialized hardware that uses quantum annealing to tackle these complex combinatorial problems.
How does D-Wave's approach differ from the theoretical concept of quantum annealing?
Well, they've built systems that leverage the natural tendency of a quantum system to settle into its lowest energy state. And by mapping a combinatorial problem onto the energy landscape of their quantum hardware, they can use annealing to find the optimal solution, which is represented by the lowest energy state.
So it's almost like letting nature do the optimization for you.
Yeah, it's pretty clever.
Yeah, it's pretty clever. And the potential applications are vast. I mean, Schneepat mentions pilot projects in areas like logistics and finance where quantum annealing is already being used to solve real-world optimization problems.
Right.
It sounds like these quantum annealing systems are actually being put to work.
Yeah, it's not just theoretical.
It's not just a theoretical concept.
No. And it's not just QGD and quantum annealing. Schneepat's essay covers a whole bunch of other quantum optimization methods, each with its own unique strengths and potential applications in AI.
Like what? Can you give us a taste of some of these other methods?
Sure. There's the quantum approximate optimization algorithm, or QAOA, which focuses on finding good approximate solutions to complex problems, even if they aren't the absolute best.
So it's kind of a more pragmatic approach,
Right.
acknowledging that sometimes A good enough solution,
Yeah.
found quickly,
Yeah.
is more valuable than a perfect solution that takes forever to compute.
Exactly. And then there's variational quantum optimization, or VQO, which is kind of a hybrid approach combining the power of quantum computation with classical optimization techniques.
So it's like a team effort
Yeah.
where quantum and classical computing are working together to
Right.
tackle the problem from different angles.
Exactly.
What else?
There's also quantum-assisted hyperparameter tuning, which leverages quantum algorithms to optimize the settings for AI models.
Okay.
And there are others like quantum-enhanced stochastic gradient descent, which, enhances a popular classical method with a quantum boost. And even quantum-inspired evolutionary algorithms, which kind of take inspiration from Darwinian evolution to guide the optimization process.
So it's like we have this whole toolbox of quantum optimization methods at our disposal.
Yeah.
Each with its own unique strengths and potential applications in AI. But Schneppet doesn't just focus on the theoretical aspects, does he? He also talks about the practical implications of these methods.
He does, yeah. He discusses some really exciting pilot projects and real-world applications of quantum optimization in various fields.
Okay, I'm definitely intrigued. Let's delve into those real-world examples in the next part of our deep dive.
Welcome back,
To the deep dive
where we're exploring the world of quantum optimization for AI.
with Jurgo Schneppet as our guide.
And in this part, we're going to look at some of the real-world applications
Okay.
that Schneppet highlights.
I'm ready to see how this quantum magic is actually being used.
Well, Schneppet mentions several pilot projects in areas like logistics and finance.
Logistics makes sense. We talked about those complex delivery route problems earlier. Is that what he's referring to?
Yeah, companies are exploring how to use these quantum algorithms to optimize those delivery routes, taking into account traffic patterns, weather conditions, all sorts of factors.
So quantum computers could help those delivery trucks navigate more efficiently, save time and fuel.
Exactly. And in finance,
Right.
Schneppet discusses how quantum optimization is being used to manage investment portfolios.
How does that work? I mean, finance is all about crunching numbers. How does quantum computing fit into that?
It's about finding the best possible allocation of assets within a portfolio given a set of constraints and risk tolerances.
So it's like a supercharged version of those financial modeling tools that analysts use.
In a way, yes, but quantum computers could handle much larger data sets and more complex models, leading to more sophisticated and potentially more profitable investment strategies.
That's fascinating. Schneppe also mentioned pilot projects in AI, right? What kind of applications are we talking about there?
One area he highlights is the use of quantum algorithms to speed up the training of neural networks.
Can you elaborate on that a bit? How does quantum computing actually accelerate the training process?
Well, training a neural network involves finding the optimal set of parameters, which can be a very computationally intensive process. Quantum algorithms could potentially find those optimal parameters much faster than classical methods.
So we could train AI models in a fraction of the time it takes today. That's a pretty big deal.
It is, and Schneppet suggests that this could have a major impact on the development of new AI applications, particularly in areas where training times are currently a bottleneck.
Like, what kind of applications could benefit the most from this quantum speed boost?
Areas like natural language processing, computer vision, drug discovery, just to name a few. These are fields where we're dealing with incredibly complex models and massive data sets.
So quantum optimization could help us unlock the full potential of AI in these fields by removing those computational constraints.
Exactly. And Schneppet also discusses some other exciting possibilities, like using quantum algorithms for hyperparameter tuning.
We talked about that earlier. It's basically about finding the best settings for an AI model.
Right? Yes, and it can be a very time-consuming and computationally expensive process. Especially for complex models, quantum algorithms could streamline this process, leading to more efficient and effective AI models.
It sounds like quantum optimization has the potential to impact almost every aspect of AI development.
It does, and Schneppet paints a very optimistic picture of the future, highlighting several trends and breakthroughs that could accelerate the adoption of quantum optimization in AI.
Okay, let's shift gears and talk about those future trends. What does Schneppet see on the horizon for quantum optimization in AI?
Well, he's particularly excited about the development of error-corrected quantum computers.
We touched on that briefly earlier. It's basically about making quantum computers more reliable.
Yes, current quantum computers are very sensitive to noise and errors, which can limit their performance error correction techniques aimed to mitigate these issues, making quantum computers more robust and scalable.
And why is this so important for AI applications?
Because AI problems often require very complex computations that can be easily disrupted by errors. Having error-corrected quantum computers would make it possible to tackle those problems with much greater confidence and accuracy.
So it's a crucial step toward building quantum computers that can actually handle the demands of real-world AI applications.
Precisely. And Schneppet also discusses the concept of achieving quantum supremacy.
That's the idea of quantum computers outperforming classical computers on certain tasks, right?
Yes, and while it's already been demonstrated in a limited sense, achieving quantum supremacy on a broader scale would be a major milestone.
Why is that? What would it mean for the field of AI?
It would demonstrate the undeniable power of quantum computing and pave the way for even more ambitious AI applications. It would see that quantum computers are not just a theoretical curiosity, but a practical tool that can solve problems that are simply beyond the reach of classical computers.
That's pretty mind-blowing. What else does Schneppet envision for the future of quantum optimization in AI?
He talks about the growing importance of hybrid systems, combining the strengths of quantum and classical computing.
We discussed this earlier as well. It's about using the right tool for the right job, right?
Exactly. Quantum computers are not meant to replace classical computers entirely. They're more like specialized processors that excel at certain types of computations.
So a hybrid system would use a quantum computer for the tasks that are best suited for it, like optimization, and a classical computer for everything else.
Precisely, and Schneppet believes that this kind of collaboration will be essential for unlocking the full potential of quantum optimization in AI.
It makes sense. It's about leveraging the strengths of both technologies to create a more powerful and efficient system. What else is on Schneppet's radar?
He also emphasizes the importance of continued research and development in both hardware and software.
That's a given, right? Mm-hmm. We need better quantum computers, better algorithms, and better tools to make all of this work.
Absolutely. On the hardware front, researchers are constantly pushing the boundaries of qubit technology, exploring new materials and designs to create qubits that are more stable, controllable, and scalable.
It's like a race to build the ultimate quantum computer.
What about the software side of things?
Well, on the software front, developers are creating new quantum programming languages, libraries and frameworks that make it easier for researchers and developers to write and execute quantum algorithms. So it's becoming more accessible, less of a black box for those of us who aren't quantum physicists.
Exactly. These tools are crucial for building a thriving quantum ecosystem and attracting more talent to the field. And of course, there's the ongoing development of new quantum algorithms specifically designed to solve AI problems.
So we've got the hardware getting better, the software getting smarter, and the algorithms becoming more powerful. It sounds like all the pieces are falling into place for a quantum optimization revolution in AI. But before we get too carried away, let's take a step back and consider the broader implications of all of this. Schneppet also touches on some potential challenges and considerations, doesn't he?
He does, and in the final part of our deep dive, we'll explore those challenges and wrap up our discussion of Schneppet's insights.
Okay, sounds good. Let's dive into that in the next part. Welcome back to the Deep Dive,
where we've been exploring the potential of quantum optimization for AI.
With Jirgo Schneppet's essay as our guide, we've covered a lot of ground.
Yeah.
From the basic principles of quantum optimization to some exciting real-world applications and future trends. And in this final part, we'll wrap up our discussion by looking at some of the challenges and considerations that Schneppet highlights.
Okay.
I'm curious to hear what he has to say. Every new technology comes with its own set of hurdles, and quantum computing is no exception.
Right. One of the key challenges Schneppet mentions is the issue of scalability.
Can you expand on that? What does he mean by scalability in this context?
It's about building quantum computers that can handle increasingly complex problems. Current quantum computers are relatively small in terms of the number of qubits they have.
And qubits are those quantum bits that we talked about earlier, the fundamental building blocks of quantum computers.
Exactly. And the more qubits you have,
the
more powerful your quantum computer becomes, but scaling up the number of qubits while maintaining their stability and coherence is a major engineering challenge.
So it's not just about adding more qubits. It's about making sure they all work together harmoniously without losing their quantum properties.
Precisely, and Schneppet points out that this is an area where significant progress is needed before we can see the full potential of quantum optimization for AI.
What about the development of quantum algorithms? Is that also a challenge?
Yes, it is. While there's been a lot of progress in developing quantum algorithms for specific problems, there's still a need for more general-purpose algorithms that can be applied to a wider range of AI tasks.
So we need algorithms that are more versatile.
Right.
more adaptable to different types of AI problems.
Exactly. And Schneepat emphasizes the importance of continued research in this area, exploring new algorithmic approaches that can take full advantage of the power of quantum computers.
So we've got the hardware challenges, the algorithm challenges, anything else that Schneepat sees as a potential hurdle.
He also talks about the need for better software tools and infrastructure to support the development and deployment of quantum optimization solutions.
Makes sense. We need the right tools to make it easier for researchers and developers to work with quantum computers and algorithms.
Right, and Schneepat points out that this includes things like quantum programming languages, libraries, and cloud-based platforms that provide access to quantum hardware.
So it's about building a whole ecosystem around quantum optimization.
Yeah.
Making it more accessible and user-friendly.
Exactly, and Schneepat believes that this is crucial for driving innovation and adoption in the field.
So it's not just about the technology itself.
Right.
It's about creating an environment where that technology can thrive and reach its full potential.
Precisely, and Schneepat's essay does a great job of highlighting both the opportunities and the challenges that lie ahead for quantum optimization and AI.
It's been a fascinating deep dive. We've learned a lot about this emerging field and its potential to revolutionize the way we build and train AI.
And while there are certainly challenges to overcome, the future of quantum optimization for AI looks incredibly promising.
So as we wrap up our exploration of Schneepat's insights, what are some key takeaways for our listeners?
Well, I think the main takeaway is that quantum optimization has the potential to significantly enhance AI capabilities, enabling us to solve problems that are currently intractable for classical computers.
And while we're still in the early stages of development, there's a lot of exciting progress being made in both hardware and software. And with continued research and development, quantum optimization could become an integral part of the AI landscape in the years to come.
Absolutely.
So it's definitely a field to watch closely. And if our listeners want to delve deeper into this topic, we highly recommend checking out Schneepat's full essay.
Yeah, it's a great read.
It's a thought-provoking read that offers valuable insights into the future of AI. Thanks for joining us on the deep dive. Until next time, keep exploring.